Hello everyone, this is Professor Iris Miano giving you your week 13, day 25 lecture video. And in fact, this is the very last lecture video that you'll have to watch for this class. Woohoo! Almost finished here, folks. So, you'll notice that it is on volume and surface area. So these two sections deal with three-dimensional figures. Volume, as a construct, is three-dimensional in that all of the final answers that you'll be calculating in order to get to a volume calculation will involve the units raised to a third power. Three-dimensional, that means an exponent of 3. Whereas surface area is going to be an item that involves three-dimensional figures, but it's a two-dimensional construct. It's kind of like if you were to paint the outer edges of a three-dimensional figure, how much paint would you need in order to, cover that particular object? Or, think about wrapping a present without making any folds or something like that. If you just needed exactly enough paper to cover the item, how much paper would you need? That sort of a thing. As far as the visual is concerned, I hope that's helpful. But yeah, so while both the volume and surface area sections that we cover involve three-dimensional figures, the volume is a three-dimensional construct while surface area is a two-dimensional construct. So it can get a little bit confusing towards the end, so hopefully we can keep that straight and get it all worked out well. Okay, but let's first dive into volume. Now for this we need, and this will be true for the surface area as well, many new formulas. So stick with me here, we're going to introduce them individually, but first I want to introduce some elements of some of these three-dimensional figures that require the presentation of new terminology. So here, the first type of three-dimensional figure that we're going to introduce here is called a prism, and prisms can have various different looks to them. But basically they have these general elements. They have two bases that are the same shape. Now for this particular example prism, this prism is a triangular based prism. Okay, so notice that the top base and the bottom base are both triangles, whereas the lateral faces are all parallelograms, or in the case of regular, regular is not the wrong term, but a right parallelogram is going to be a rectangle. So sometimes the rectangles, as long as they have a right angle in the corner, but otherwise they might be slanted a little bit, in which case the prism would have a quintessential parallelogram lateral faces. So those are the sides. So notice for this triangular based prism, there are 1, 2, 3 lateral faces. Okay, cool. Now, the other three-dimensional figure that there's several that we're going to introduce here. Another one is called a pyramid. So here, pyramids have a couple of distinct elements to them in regard to comparing them to prisms. For instance, pyramids only have one base. Here in this figure, we have a pentagonal-based pyramid. Excuse me, I was about to say prism, but I meant pyramid. We're talking about pyramids. They have one base, and this base pyramid happens to be a pentagon, but always the lateral faces of a pentagon are always triangles. Okay, so notice that we have 1, 2, 3, 4, 5 triangle lateral faces here, and you'll always have as many lateral faces as there are edges to your as you have edges to your base, and that'll be true for pyramids and prisms alike. So notice that if I can go back a little bit to the prisms example, that there were 3 parallelogram, technically in this case rectangle, lateral faces, and that was a consequence of the base being triangles, right? So the base having 3 edges dictates that there will be 3 lateral faces. Okay, yes, and the very same thing is true for pyramids. This pyramid has a pentagonal base, so that means that there are 5, one for each edge of the pentagon base, 5 triangular lateral faces that come to a point. And if it is a right pyramid, we'll talk about a right versus oblique pyramid and prisms, then the point that it touches all at the top here will be directly above the center of the base. Anyway, that's something that we'll get into it a little bit. The thing you want to note here is that if we're talking about prisms, we have two bases and parallelogram lateral faces versus a pyramid that has one base and triangular lateral faces. Then there are cones. Cones have a circular base, right? And a kind of a skirty looking lateral surface, something that we don't get into until later on in the surface area discussion. But for our purposes, the main things that you need to glean in regard to calculating the volume of a cone is going to be the radius and the height. You'll find that those are the only two measurements that you need. We'll get to the formula specifically in just a little bit. And then, of course, there's also spheres that we will be talking about the volume of in this section, in which case the only thing that you're going to need to calculate the volume of a sphere will be the radius. So stay tuned for that formula in just a little bit. Next, I wanted to really give you guys a pretty clear indication of what it means to be a right prism. So here is a hexagonal based prism. And this is called a right prism in example A, because notice that the parallelograms, quote unquote parallelograms, that are the lateral edges, and notice there's 6 of them. Here's 1 lateral edge, 2 lateral edge, 3, 4, right? 5, the back edge here, and then 6. So there are 6 lateral edges because the base is a hexagon which has 6 edges. Okay, and what I want to really point out here is that a right prism is going to have technically rectangle lateral edges, whereas an oblique prism that you see in example B here is going to have more of that quintessential parallelogram look to their 6 lateral edges. Okay, cool. So feel free to add figures, drawing them to the best of your ability on your lecture notes. I know there's a space provided for this. So we could talk about tips and tricks for drawing these things yourself if you're interested in it, but just know that you're not going to be asked to draw these things in your upcoming exam 5, just so that we're all clear. Anywho, let's get into the volume formulas. So there is a general form for the volume of a prism, a cube, a solid, or a cylinder. Something that we haven't talked about, solid or cylinder, right? So there's these two right here are going to be, well, all 3 of these are going to be given to you explicitly, but these are all basically different types of prisms. It's like you could get a little bit more specific if you're talking about a cube, a solid, or a cylinder. Cylinders are circular based, but they have 2 bases like a prism is originally defined. So the general form of the volume formula goes like this: area of the base times the height. If you can keep that straight, I think it'll help you memorize, or rather internalize, the enormity of the number of volume formulas that you have to really be able to recall from memory. Area of the base times height, that's the general flow of it for volume formulas involving prisms, specifically cubes, solids, and cylinders. Let's start with the cube. That's the easiest one, I think, to remember, because all of the edges, the outer edges of your cube, are going to be the same length. We're letting it be represented by lowercase s. So you'll take that lowercase s value and raise it to the 3rd power, or cube it, right? It's kind of in the name. So that'll give you your volume measurement, and make sure that the units also get cubed or raised to the 3rd power. And you could call the units cubed or cubed units, depending on what they are, specifically centimeters, inches, miles, that sort of thing. Okay? Moving on to a rectangular solid. A solid, right, has rectangular faces all the way around. The bases are rectangles, the edges are rectangles, or might be squares as the case may be. In any event, the volume formula is you take the length, the width, and the height, and you multiply them all together. That's one of the easier ones for sure, but not as easy as even the cube, where you just need one side length and then you cube it. So this one, you take the three side lengths, which may or may not be distinct, and you multiply them all together. And don't forget your three-dimensional units at the end. Moving on to prisms. Now this is where we need to get a little bit more, general, because the bases could be triangles, they could be hexagons, they could be nonagons, they could be dodecagons, get all crazy with it. We won't get any crazier than the usual things that we have area formulas for, so don't worry about that. Mostly stick to squares, rectangles, and triangles for bases, okay, just so you know. But yeah, you'll need your height, you'll need the area of the base, and you'll multiply them together and you'll get your prism. So notice that for this volume formula, we have to be very vague about the area of the base. So we just categorize that with this capital B. And depending on what kind of base you have, that's where you'll put in the area of it, component of that formula, and just multiply it by the height, and that'll give you the volume of the prism in question. Okay, great. Now for the cylinder, cylinders have circular bases, and that could be a right cylinder like you see here in this blue one, or it can be an oblique cylinder, right? And you'll just want to get the height calculation, which will be pretty much the altitude, okay, if you were to transfer that idea over to this three-dimensional space. And again, it's area of the base times height. Notice that the area of the base is this pi r squared, right? If it's a circular base, the area of a circle is pi r squared, so you need this radius with the regard to the base, and you'll multiply it by the height. So notice that when you're looking at this figure here, whether it's the blue one or the orange one, the base kind of looks like an ellipse or an oval, a stretched out circle, and that's just to give this particular figure some three-dimensional depth to it. But the general understanding is that this figure has a circle top and a circle bottom, okay? So hopefully everybody takes that into account when they're looking at these figures, and that was maybe terribly obvious and didn't need to be stated. In any event, I just want to make sure we're all on the same page. So again, the volume formula for a cylinder is area of the base times the height. Okay, for pyramids and cones, there is a basic form for this formula for the volume, and it's as follows: 1/3 times the area of the base times the height. So, it's very similar to the various types of prisms. You just take 1/3 of it. Now, why is that? Well, there's a video proof for this that I'll share in class when we meet about these sections. So we'll have a little bit of a visual, being able to explain that relationship when we see each other in class. Okay, but anyway, this is the basic idea: 1/3 times the area of the base times the height. So for a pyramid, let's say we have this square-based pyramid right here, or it doesn't really matter what shape the base is, because we're going to just, in our volume formula, generically let that uppercase B represent the area of the base. Now, if this base, it looks like it's a square, but let's say it was specifically given to us as a square, so you would have side squared as the thing you would substitute in for your capital B. And you take 1/3 of it, multiply by this height, and there is your volume for that pyramid. And then for a cone, you'll have a circular base, so that'll be 1/3 times the area of that base, pi r squared in this case, times the height. And that's how we derive this volume formula for a cone. Okay, moving on. We'll have some examples of this right after we introduce a sphere volume formula. Sphere is going to be, here's a sphere, and the volume formula is going to be 4/3 pi r cubed. How do we get this? Great question. There are videos on YouTube that go into the derivation of this formula. If you're interested in that sort of a thing, please, by all means, you can YouTube search keywords sphere volume formula derivation. And if you do that, you'll get some wild visuals for that. But, for our purposes, we just need to get to know this formula. So if you need to find the volume of some sphere, the only measurement that you need in regard to the sphere is its radius. So take in that radius, cube it, multiply it by pi, and factor 4/3. And there you have it. And chances are, because there's a pi, anytime in any of these formulas there's a pi concerned, you just want to have that pi kind of come along for the ride, because I want you to always be giving exact answers at any point, and particularly when your answers, what's the phrase I'm looking for, are meant to be exact or should be given in terms of pi. Okay, now I think that's all the formulas. Let's go ahead and start with some examples. Let's find the volume of this particular prism. So you'll notice that it's a triangular based prism, and it's a right prism in that the lateral faces are rectangles. Okay, so it has a height of 4 inches, and it's a 3, 4, 5 triangle for the base here, and also the base is it's a congruent triangle for the base, the bottom base, that is. Now, 3, 4, 5, does that sound familiar to you? Okay, it should. And just by virtue of recognizing the Pythagorean triple in these side lengths for the base of this prism, we can go ahead and recognize that we have a right triangle is a 3, 4, 5. So that being said, we know that the area of the base, big B, is going to be half of the base times the height, which is, the base of the triangular base itself is, it's going to be probably this 3 or this 4. It doesn't matter which one you say is the base or the height. It doesn't make any difference because we're dealing with a right triangle. So you just take 1/2 of those two measurements, the 3 and the 4. We just know that the 5-inch side is not the base or the height because it's the hypotenuse. So that's why we're just going to have, it doesn't matter which one, the 3 or 4, you designate as the base of the triangular base or the height. It's the same either way. So that'll give you the 6, which will be the area of the base. Now notice that I am not bothering with affixing the units, which would be inches squared here, but because I'm going to have to multiply it by the height of the prism, which is this 4-inch edge as well, right here. So when we're talking about height of the prism and height of the triangle, these are two separate things. So it probably would behoove us to slightly modify the original area of the base formula to have that height be h sub 1, and the volume formula, that height, which is separate but happens to be the same number, which is extra confusing, but that is technically a different height, so it warrants a separate subscript here. So we'll take the area of the base that we found to be 6 square inches, multiply it by the height of 4 inches, and that's how we get 24 inches cubed. Remember, we're talking volume here, which is the 3-dimensional construct, so we need to move into the idea that our units should be 3-dimensional from now on in this section. Of course, when we talk about the last section in 10.5, where we talk about surface area, even though we're dealing with 3-dimensional figures in that section, we are doing so in a 2-dimensional construct. Extra confusing, so we'll have a fun time making sense of that when we get there. But let's go ahead and entertain some more examples, still in the realm of volume. Let's find the volume of this solid. So remember, volume for solids, prisms, cylinders, cubes, all that stuff, it's area of the base times the height. The base appears to be a square base, and then the height is 8 centimeters. So you literally just multiply 4 times 4 times 8, the length, width, and height respectively. And there you go. And that's how you can go straight to, with relative ease, I think, this volume of 128 centimeters cubed. Okay, cool. So there you have it. That one's relatively quick and easy. Solids are like that, just length, width, height. Multiply them all together in units cubed, and then you're done. Okay, moving on to the next example. Ooh, let's go ahead and find the volume of the square-based pyramid. So the area of the base will be 3 times 3, right? Height 5 feet, so that gets thrown in the mix. But then remember, you need to multiply a factor of 1/3 in there as well because it's a pyramid. So the area of the base, that'll be this 3 times 3 business. The height was 5. Don't forget your factor of 1/3. These kind of cancel each other out, right? Because they're multiplicative inverses right here, the 1/3 and the 3. And so that's how we got a 15, the remaining 3 times the 5 feet cubed. Okay? Cool. So hopefully that's terribly straightforward. And if it's not, we could talk about it more in class. Let's move on to the next example. Let's get the volume of this circular cylinder. Leave your answer in terms of pi. Remember, it doesn't matter that this cylinder is oblique. It's still going to go according to the mantra of area of the base times the height. Because cylinders, prisms, solids, cubes, they all work in that similar way. Area of the base times the height. So take the area of the base pi r squared and multiply it by the height. Plug in the numbers. 6 goes in for r, 13 goes in for h. Multiply it all together, let pi come along for the ride, and you get 468 pi millimeters cubed. Yep. Pi stays there. Millimeters gets raised to the 3rd power because we're talking about volume. Okay, moving on to the next. Let's find the volume of this cone. Now remember, cones, pyramids, the mantra is that volume is 1/3 times the area base times the height. So referencing the appropriate formula, plug in 8 for r, h is 21, simplify, 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 let pi come along for the ride, and recognize that the units get cubed because, again, we're talking volume. And that's all there is to it. Like, there's not a lot of crazy, there are some algebra nuances here that I am skimming over. So if this example is something you'd like to talk about a little bit more detail about as far as like how the simplification occurred from this step to this step, we can do that in class. Okay, but for now, let's go ahead and move on to the next example. Okay, we're going to get wild with it here. What is the volume of this sphere, aka the Earth? Right? So the diameter of Earth is approximately 7,920 miles. So the units are miles, and this is the straight across distance from one end to the other end going through the Earth, okay? And we're going to leave our answer in terms of pi. So check this out. Let's take the fact that we have this diameter measurement. We got to cut it in half in order to get the radius. Because remember, the radius is the only thing that you need in order to calculate the sphere volume. So what was the volume of the sphere formula again? Well, it was 4/3 pi r cubed. Go ahead and plug in for for r. We don't plug anything in for pi. Pi just comes along. R, though, is 3,960 miles, approximately. And we're going to cube it. Oh, Lord. So that's going to be a really big number. But once you simplify it with the 4/3, right, you're going to have it be, what is this, 82,798,848,000 pi miles cubed. Yikes! So the fact that we left this answer in terms of pi to get an exact answer, or, because it was explicitly asked of us to do that, just notice that as big as this number is, it's got to be at a little bit more than tripled in order to get the actual, or not the actual, but the approximate value here. It's a wildly big number. Anyway, but that's what we would expect. The Earth is a big place and it's got a large, large volume. So there you have it. So that's just a bit of fun. I would never put anything so wildly complicated or such big numbers that you would really need a calculator in order to calculate on an exam. That's just something that I thought would be kind of interesting for us to very briefly discuss in this lecture video. Okay, but moving on. I believe we are in the next section now. We are going to discuss surface area. Now, again, and I can't stress this enough, how, confusing this can get, because we are talking about three-dimensional figures for this section, but we're going to talk about the two-dimensional construct associated with it. Surface area, it's in the name. If we were trying to cover the surface of these three-dimensional figures, how much area would we need in order to do so? That is the jam for this section. So there are general rules for these surface area formulas for different types of three-dimensional figures, and that's what we're going to introduce first, okay? So generally for prisms and cylinders, we have this kind of a setup here. The total surface area, TSA is sometimes the way it's acronymed, is going to be twice the area of the base plus the lateral surface area. What's the lateral surface area? Well, that'll depend, you know, on what the dimensions are. They'll basically be all of the three-dimensional figures that we talk about for the surface area section for 10.5, they're all going to be right, which means that they're going to have rectangular lateral faces, okay? So it's going to be a series of rectangles here, okay? Cool. So let's go ahead and discuss that with a, this is a solid, right? So there's the two bases and there's the lateral surface area, right? It's going to be four, you know, rectangles there, but then the two top and bottom, the two area of the bases are going to be associated with that first term's calculation. Okay, so let's get a little bit more specific for a right prism, okay? That'll be the total surface area, TSA, is 2 area of the bases plus the lateral surface area, guys. We can shortcut it to the height times the perimeter of the base. This lowercase p, that is designated shorthand for the perimeter of the base, okay? So where this capital B is area of the base, lowercase p is perimeter of the base, okay? So if the prism has a, you know, triangle base, right, then the perimeter will be the 3 edges of that base added together, okay? And then multiply that by the height, and that gives you the lateral surface area in the second term. Okay, so let's go ahead and entertain this for this particular rectangular prism that happens to be a solid, okay? So let's take the 2 area of the bases, that's the 15 times 3 will be the area of the base, and then the height will be the 4 centimeters, and then the perimeter of the base will be 15 plus 3 plus another 15 plus another 3. So, but let's go ahead, we can also do 2 times 15 plus 2 times 3, which is, you know, the perimeter of a rectangle. But it doesn't matter how you do it. You can do it the long way that I first mentioned or the short way, which is directly using the formula. So let's go ahead and use our formula here, plugging in these specific values. Simplify, 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 and we get 234 centimeters squared. Yes, I know. It's a little bit, you know, confusing in this section. All of your units for surface area are going to be square units because it's area. Even though it's in regard to a 3-dimensional figure, it's a 2-dimensional construct. 3-dimensional figure, 2-dimensional construct, that is surface area. Okay, cool. Great, so there's our first example there. Let's go ahead and introduce the next type of 3-dimensional figure. Let's talk about, or actually, sorry, yeah, then that'll be a right circular cylinder. So that'll be 2 area of the bases plus the lateral surface area, right? But specifically for right circular cylinders, it's going to be this, 2 pi r squared plus 2 pi r h. I know, it's a lot. And these 2 terms are incredibly similar in the way that they're presented, so it's very easily, you know, it's easy to get this confused. But this is something you'll want to get to know very intimately. And so let's go ahead and use this formula to find the total surface area of this cylinder right here, this kind of mustardy, Dijon mustardy yellow colored one right here. And let's give an exact answer. And the reason why we have this caveat here is because this formula is riddled with pi's, irrational numbers. So we want to make sure that we have our final answer in terms of pi to give homage to the fact that we're supposed to have an exact answer. No 3.14s here, okay? So let's go ahead and recognize that our r value is 6 and our height, our h value is 5. So plug and chug, folks. Put in a 6 for r, a 5 for h, and simplify, simplify, 2 steps of simplification if you did it my way, and you have 132 pi feet squared. Notice that these two terms are both like terms. They're both pi terms. I have 72 pi's over here, 60 pi's over there. I can certainly add them together and get 132 pi's total. Affix the appropriate units. Remember, it's a two-dimensional construct, and the distance measurement is in feet. Okay? So hopefully that all makes sense and feels good, but if it doesn't, let's talk about it in class. Next example. Let's find the total surface area of a pyramid or a cone. We will need slant height, which is a brand new measurement for us. Okay? So consider these two example polyhedrons, okay, which is a generic term for any kind of three-dimensional polygon. So if we have this particular square-based pyramid or this circular-based cone, these distances that you see in red are going to be your slant height, which is designated by the letter lowercase s, okay? So it's just going to be that outer edge from the peak of your cone to the outer edge of the circle. That's going to be your slant height. Or if you have some sort of a pyramid, it's going to be the altitude of the triangular lateral face, so to speak. Okay, so because it's meeting the edge of the base of the triangle perpendicularly. That means it's the altitude. Okay. Very good. So let's keep that in mind to find the total surface area of a right regular pyramid. Here is the formula for it. It's the area of the base plus 1/2 of the perimeter of the base times the slant height. So the perimeter of the base is going to be pi r squared if we're talking about, it's pyramid. So that's going to be whatever shape the base is, it's just going to be the distance all around it. Sorry, it's a little bit different. We talk about cones in the next one, okay? So let's consider this particular square-based pyramid and find the total surface area of it. So the area of the base is going to be this 2 by 2 square base, right? Plus 1/2 of the perimeter of the base, 2 plus 2 plus 2 plus 2, right? Times the slant height, which they happen to give us, of 3 yards. So here's me just plugging in all of the values. The area of the base being 2 squared, 4 times the length of the edge is going to give me the area, the perimeter of the base. That's this p value is the 4 times 2. 4 times the length of the square. We have the 1/2 factor right there, and the slant height is the 3 right here. So hopefully everybody can see pretty clearly where all of these values are coming from the figure. And then we just simplify until we get 16 square yards. Yep, the distance unit's yards, and we have to square the units because we're talking surface area. Okay, moving on to the next example. Let's find the total surface area of a right circular cone. The general formula will be as follows: area of the base plus we have to take the area of the lateral surface there, which is pi r times the slant height. So pi times the radius times the slant height, that gives you that lateral surface. If you were to, like this edge here, this upper edge, if that makes sense. So find the total surface area of this cone, give an exact answer. One thing you might notice is that in this figure here, we're not given the slant height, are we? We're just given the height of this cone and the radius. But it's a right regular cone, which means that the edge of this height of the cone and the radius form the legs of a right triangle. And it's a 312. It looks like it's the makings of a Pythagorean triple. Does anybody know what the hypotenuse of that right triangle is, and therefore the slant height of the cone itself? It's 13 millimeters, right? It's a 5, 12, 13 right triangle, a Pythagorean triple. So sometimes these will come up in some of these chapter 10 things. So just heads up, Pythagorean triples are definitely coming into play with this chapter 10 material. having that slant height now, we can plug in 13 for S, 5 for R, and then simplify down to getting a total surface area of 90 pi millimeters squared. Okay, cool. So that one is straightforward, so long as you know that you need to calculate the slant height and you recognize that the right triangle formed by the height and the radius are 2 out of 3 of a Pythagorean triple. Or you can use the Pythagorean theorem in order to calculate the hypotenuse of this right triangle, which is also the slant height of the cone. Cool. Moving on. Let's learn the surface area formula for a sphere. It's 4 pi r squared, which is painfully similar to the volume formula for a sphere, which is 4/3 pi r cubed. So keeping those two separate and distinct and learning them both is somewhat challenging, so good luck with that. And if you're interested on the derivation of the surface area formula, of course, there are YouTube videos on that as well. We can dive into that if people are interested in class and find some good ones for that. Okay, so let's go ahead and use this formula though to find the surface area of this sphere with a 5-inch radius. So again, just like the volume formula for a sphere, the only measurement that you need for it is the radius. So plug that into your R value and simplify, and Bob's your uncle. There, it's 100 pi inches squared for this particular calculation, because that 5 squared gives you 25, multiply it by 4, that's 100, pi comes along for the ride. All right, and that's it for that one. Let's go ahead and move forward. The next thing, and this is the very last example of this section, the very last example of, the lecture videos for this class. So here we go, the end of an era. Let's go ahead and find the area of the base of the right regular pyramid that you see here. So the base is a right regular pyramid. The area. Okay, so that means when it's, and then find its total surface area. Give exact answers. The measurements are in meters. So they didn't bother, I scanned this from the textbook, and they didn't bother to put M's after the 9 and the 6, but we know that they're meters based on this prompt here. And if it's a right regular pyramid, then that means, if it's regular, then that means the base is going to be an equilateral triangle, okay? So if one of the edges, so I went ahead and did a cross section just of the base there, just rewriting it as a little bit of a flat surface, and notice that the one edge is of length 6, but since we know that it's a regular pyramid, we know that the base is actually an equilateral triangle, which has edges all of length 6. We can use what we've learned about equilateral triangles and altitudes there to get the height of this a triangle, which will end up being 3√3. And this is a consequence of knowing that this altitude here is a 90-degree angle, right, is formed, it's a right angle. And this angle right here has to be 60 degrees because it's an equilateral triangle, so that means this angle has to be 30 degrees, the bisecting of the 60-degree angle up here, and that means this hypotenuse value has to be of length 6 because that was given to us. This edge from the altitude to this vertex is going to be 3, so the height has to be 3 times √3. So that's how we're getting that value there. So what's the area of this base? It's going to be 1/2 base times height. And now we have all of those measurements. 1/2 base measure is 6 meters, and the height measure is 3√3. So go ahead and throw all of that stuff together to get the area of the base, which I'm denoting here as by capital B. 1/2 times base of 6 times height of 3√3. That gives you 9√3s, and meters squared is appropriate here because we are finding the area of the base. That is part of the things that were asked of us. Then find its total surface area. Well, we can do that now that we have the area of the base, and then we have to multiply that by, take that area of the base and then add to it 1/2 of the perimeter of the base times the slant height. And they happened to give us the slant height, didn't they? They gave us this 9-meter slant height here. That was very kind of them. So let's take our area of the base that we just calculated as 9√3s and then add to it 1/2 times the perimeter of the base. Remember, it's an equilateral triangle, so it's 3 edges times a length each of 6. 18 will be the perimeter of the base, and then that slant height 9 came from this measurement that was given to me here. Multiply all this stuff together, simplify as much as you can, and that's it. You actually cannot add this 81, which ends up being the resulting product of the second term here. You can't add that to the 9 root 3s because the root 3 is an irrational number. And as we've seen with a lot of these other examples, when it involves pi, some other irrational number, you cannot add rationals with irrationals if you're trying to present an exact answer, which is what we're trying to do here. So to keep the 9 root 3 and the 81 separate within a plus sign in between, but do remember to affix your final answer with the appropriate units, which will be meters squared. And that's a wrap, okay? So if in class you'd like to see any of these examples with a little more detail, or any of these homework problems with some further detail, or I can present them from start to finish, by all means just ask. I am here to help you, and I would love to show you all of the details associated with finding the solutions to these problems. And that's it for the semester. This is your last lecture video. Good job. You watched them all, I hope. Cool. Thank you so much for your time and attention, and I will see you soon in class.